So thank you, Sarah and Paolo, for the invitation, and all the people who are involved in the organization. Thank you for this conference. I'm happy and honored to be here. Last time I was in Siena was for the AAA 99, so the end of February 2020, so just a few weeks before the lockdown.
Yes.
And yeah,
That's exactly when the first COVID case was.
Yeah. Exactly. So I find this topic appropriate because in this period I discovered that the word positive can have different meanings depending on the context. It can be something. It can be something good, like a positive referee report, or maybe something not that good, like a positive copy test. So, question: what about a positive MV-algebra? Is that good or bad? Well, in this talk, I want to share some results about positive MV-algebras. They were introduced very recently by Gabriel, Gibson, and Krupa. And I'm sharing some results, so that should have to develop this theory. So at the end, I will mention some future work that I would like to do, and if someone is interested, I'm happy to work together. And hopefully at the end, you will have your own opinion whether this is something good or bad. Let's see. So just roughly speaking, so a rough idea of what positive MV-algebras are. These are to MV-algebras what bounded distributive lattices are to Boolean algebras. Boolean algebras are the algebras of classical propositional logic. And bounded distributive lattices can be thought as the algebra of the positive fragment of classical propositional logic. Here, by positive, I mean negation-free in a certain sense. I don't mean the zero-free fragments. I mean something else like the order-preserving fragments that I will comment later. Okay, and if Boolean algebras are the algebra of classical propositional logic, and the algebras are the algebras of Łukasiewicz many-valued propositional logic. So here, many-valued refers to the fact that the set of truth values is the unit interval 0, 1 instead of the two elements set. And MV of MV-algebra stands for many-valued. So if MV-algebras are the algebras of Łukasiewicz propositional logic, positive MV-algebras are the algebras of the positive fragment of Łukasiewicz many-valued propositional logic. So this study is in the framework of studies of positive fragments. So there are some other examples like introduced positive model algebras, which are model algebras without negation, or also positive relational algebras. There are studies which are relational algebras without complementation. So some history of positive MV-algebras. So in 2013, Sintra and Krupa studied some aspects of the positive fragment Łukasiewicz logic because they were interested in game theory, and positivity comes into play because winning coalitions are increasing in a sense, meaning that if I join a winning coalition, it will remain a winning coalition. And a few years later, Krupa with Javier and Gibson introduced the algebras related to this. So introduced positive MV-algebras. And I got interested because, well, I had some familiarity with MV-algebras, and also I use them to obtain a duality for certain spaces. But I will not talk about this result in this talk. Regarding motivation, so some people suggested to me that like Heyting algebras are based on bounded distributive lattices, maybe an appropriate many-valued version of high-king algebras may be based on positive MV-algebras. So to me, besides their logical interest, they are a well-behaved study case for certain results in duality theory and general algebra. So they provide some very well-behaved examples for certain general results. Okay, so before talking about positive MV-algebras, let's talk about MV-algebras. MV-algebras, so are the algebras of Łukasiewicz many-valued propositional logic, which takes 0, 1 as the set of truth values. And Chang introduced MV-algebras as the algebraic semantics in order to have an algebraic proof of a completeness theorem. Okay, I will introduce them in a second, but first let's see the main example of an MV-algebra. It's the unit interval 0, 1 with the following operations. So we have a truncated sum, or simply a sum, which takes x and y and gives you back. It cannot give you back the sum because it may be outside the unit interval 0, 1. So you have to truncate it at 1, and so it gives you back the minimum between x plus y and 1. So for example, 0.3 plus 0.2 is 0.5. It's less than 1, but 0.7 plus 0.8 is 1. And okay, so that's the first operation. Second operation, negation. So you take x and you map it to 1 minus x. So for example, not 0.3 is 0.7. And then you also take 0 as a constant. And 0, 1 with this operation is the prime example of an MV-algebra. An MV-algebra has this definition. So it's an algebra with these 3 primitive operations. And it's a commutative monoid. So it's a generalization of a Boolean algebra. So where you think of these classes, the join, the generalized join, negation and 0 as the usual operations. And it's a generalization, meaning that class is not assumed to be idempotent. So x plus x might fail to be x. Okay, and the axioms that it satisfies are that it's a commutative monoid, the double negation of x is x, x plus the negation of 0 is negation of 0, and then you have this further axiom. Well, what's important is that these 4 axioms are actually a basis for the equational theory of 0, 1. So once you have all these 4 axioms, all the equations holding in 0, 1 hold. So an equivalent definition would be MV-algebras are the variety generated by 0, 1. So it's HSP of 0, 1. Okay, and so for example, 0, 1, the unit interval, also all subalgebras of 0, 1. So some subalgebras are the 2 elements set 0, 1. Here plus coincides with join. Then we have, for example, L3, 0, 1, half 1. This is the algebra, it's closed under plus, negation, and 0. And in general, for every n which is equal than 1, we have this subalgebra Ln of which has, sorry, this should be Ln plus 1 because there are n plus 1 many elements. And it has 0 over n, 1 over n, and so on. Further example is Q intersection 0, 1. Or another example is any Boolean algebra. Here you set class as the join. Okay. And also, often I think about an MV-algebra in this way. So if you have a set x, then the set of functions from x to 0, 1 is an MV-algebra. Not every MV-algebra is of this form, but yeah, it's a good approximation to think of an MV-algebra as something like that, as an algebra of function of 0, 1 value functions.
But the operations we can do like on the results. Like
Here.
if functions.
Yeah, pointwise. You add. Yeah, if I have two functions, I add them pointwise. Yes, exactly. Yes. So, and since MV-algebras are HSP of 0, 1, well, if you remove the H, these are algebras of functions. So, yeah, MV-algebras are not. So it's a good approximation to think of the MV-algebras as algebras of 0, 1 value functions. And now every MV-algebra has a bounded distributive lattice redux. You can term define the join and the meet, and also the one is the negation of 0. And the corresponding order on the example 0, 1 is the usual order, while on the 0, 1 to the x, it's the pointwise order. One can also term define the Morgan dual of class as it's called the times, and it's in 0, 1 it behaves like this. So you take the sum between x and y, and you measure how much it exceeds 1. So you do -1, and then if it's below 0, you take 0. Otherwise, you take x plus 1 minus 1. So, for example, 0.7 times 0.8 is 0.5, while 0.3 times 0.2, if you make the sum, is 0.5 minus 1, gets negative, so you take 0. There's nothing to do with the multiplication of real numbers, but I think the notation comes from the fact that x times 1 is x. Okay, and if you want to think of class as a generalization of join of Boolean algebras, then think of times, which is the Morgan dual of class, as a generalization of the means. And an important result is that MV-algebras, which have a quite complicated axiomatization, can be understood by what is more easily understood, that is abelian lattice-ordered groups. So an abelian lattice-ordered group, we have already seen it, is an abelian group with a lattice order which is translation invariant. Some examples are R, Z, Q with an additive structure, the set of functions from a set X to R. Yeah, maybe. And the connection between abelian groups and MV-algebras is the following: that you have an abelian group and you take a positive element, so an element greater than 0, then the interval of elements between 0 and 1 is naturally kept with the structure of an MV-algebra. You can define x plus y as x plus y with 1. This still belongs to this interval, still is between 0 and 1. You can define the negation of x as 1 minus x, and 0 is the identity element of G. So some examples: gamma of R1 is the MV-algebra 0, 1. Take gamma of Z1 is the two-element Boolean algebra, which is a bounded. The two-element MV-algebra, which is a Boolean algebra. Or if you take 1 over nz, and you take 1 as a positive element, you get as the truncation, the unit interval is Ln plus 1. In general, or for a set X, you take the functions from X to R, you take the constant function 1, and you apply this gamma, you get the function from X to 0, 1, which have an MV-algebra structure. Yes.
Question.
Yes.
I can't see why the negation is above. So it's exactly what you want.
Okay. Let me think. So 0. So we have this hypothesis, and we want to prove. Let's see. For example, we want to prove that this holds. This is equivalent by concatenativity and order the fact that class is order preserving, I think it's equivalent to, let me think, to this. Sorry. Thank you.
Yeah.
And then yes, from this. And similarly, yes. Thank you. Good question. Okay, and every MV-algebra arises in this way. That is, there exists an abelian lattice-ordered group G and a positive element 1, such that the MV-algebra is isomorphic to gamma of this G1. So usually when I work with MV-algebras, I take an MV-algebra and I think, okay, there's some abelian group of whose interval is this MV-algebra. And so, for example, if I have the MV-algebra of function from n to 0, 1, with operations pointwise, then this is gamma of something, right? It's a unit interval of a certain lattice-ordered group. For example, I can take all the functions from n to r, and with a positive element 1 as a constant function 1. There is another group, another abelian group that I can take. I can also take the bounded functions from n to r, and with the same constant function 1, and still gamma of these will be isomorphic to A. So, and these two are not isomorphic. So let's say the G1, the group G1 is not uniquely determined unless you impose some further restriction. So, in fact, for every MV-algebra A, there is a canonical pair of an abelian group and a positive element, such that A is the interval of the MV of G, and this is characterized by the condition that essentially every element is bounded by some multiple of 1, which is called the unit. So this is a way to say this is that 1 is a strong unit, that is for all x in G, there is some natural number n, such that x is below n times 1. And with this further restriction, we get a 1-1 correspondence between MV-algebras and abelian lattice-ordered group with strong unit. And in fact, this is an equivalence of categories, where if you take as morphisms here, MV homomorphisms, so function that preserve all the algebraic structure, and here homomorphisms of abelian groups that preserve the unit. These two categories are equivalent. And this was what I wanted to say about MV-algebras. So let's dive into positive MV-algebra now. Or are there any questions? No. Okay, recall that positive MV-algebras are to MV-algebras what bounded distributive lattices are to Boolean algebras. Let's see more precisely what we mean. So first, what is the relationship between bounded distributive lattices and Boolean algebras? So first, the reduct with respect to the signature of any Boolean algebra is a bounded distributive lattice, and vice versa. And any subalgebra of this reduct. And in fact, these bounded distributive lattices are precisely the subalgebras of reducts of Boolean algebras. And what is one thing that is special about this signature here? Well, for example, these are order preserving, right? Not only, and these are the only order preserving terms, meaning that they generate all order preserving Boolean terms. Okay, so in a certain sense, bounded distributive lattices are the positive subreducts of Boolean algebras, where by positive, I mean order preserving. And so, analogously, positive MV-algebras are defined as the subalgebras of the redox with respect to this signature here, plus times joining 0 and 1 of MV-algebras. What's so special about the signature here? Well, these are order preserving in each coordinate. And we'll leave out negation, which is not order preserving. And moreover, they are all the order preserving terms, meaning that they generate all the order preserving terms of MV-algebras. So if you want to restrict to the order preserving fragment, then this signature is the right choice. So positive MV-algebras, in this sense, are the positive subreducts of MV-algebras. And so you can think of them as the many-valued version of bounded distributive lattices. Some examples. Well, every MV-algebra. So the redux of every MV-algebra, we have the unit interval 0, 1, and so on. Every bounded distributive lattice. Now you take a bounded distributive lattice, you set plus equals to join and times equal to meet, and you get a positive MV-algebra. And so positive MV-algebras are a common generalization of MV-algebras and bounded distributive lattices. And the way I think of positive MV-algebras usually is I think of posit x, and I take the set of order preserving functions from x to 0, 1. Right. Not all positive MV-algebras are of this form, but this is a good approximation of what a positive MV-algebra is. So maybe in what follows, you can think of this as a main example. So just to have some more examples, let's see some subreducts of the MV-algebras L3 times L3. So this is an example of a subreduct. So it's a positive MV-algebra. What does it mean? So I take 2 copies of L3, and I connect to 2 dots if I consider the pair to be in the algebra. And so this picture coincides with the subalgebra of L3 times L3, consisting of the pair 0, 0, 0, 1 half, 1 half, 1 half, 1 half, 1, 0, 1, and 1, 1. And you can think of this if you order the 2 copies. So you say this is less equal than this. These are the order preserving functions from the 2 element poset to L3. Yes, to L3. And this is closed under all the positive operations. It's not closed, it's not an MV-algebra, it's not closed under negation, but it is a positive MV-algebra. Another example is what I call the ordinal sum. You take all the pairs such that AB, such that either A equals 0, so this 3, or B equals 1, this 3. And then you get, in this case, a linearly ordered positive MV-algebra. And actually, you can do this always. You can always make you can always stack some positive MV-algebras one on top of the other. Okay. Okay, these are some examples. Now, one important tool for MV-algebras was that they were the intervals of abelian lattice-ordered groups. Now we want to do something similar for positive MV-algebras. We want to see them as intervals of some easier structure, and we can do this as follows. If MV-algebras were intervals of abelian lattice-ordered groups, then positive MV-algebras are intervals of certain lattice-ordered monoids. So here we are removing the negation. Here we are removing the additive inverse. Let's see some in details how this works. We need the notion of a selective commutative distributive monoid. This is a selective commutative monoid equipped with a distributive lattice order such that the monoid operation plus distributes of the lattice operations join and meet. Some examples are well, every Boolean group, so R, Z, Q with a class. Also, and I invite you to think this is the main example, the set of order preserving functions from a class of X to R. This is conservative, it's commutative. Again, all the operations are taken pointwise. It's distributive and it's a lattice and it's monoid. And now what is the connection between these monoids and positive MV-algebras? That if you take a constellative commutative distributive L monoid N, and you take any positive element which is invertible. So for example, if you're taking the set of order preserving functions from a coset X to R, then you can take as one the constant function 1, which is positive and invertible. And if you take the set of elements between 0 and 1, which we call this gamma and 1, this is a positive MV-algebra. And the operations here are defined as follows. So x plus y is x plus y mid 1. X times y is x plus y minus 1 join 0. Still belongs to gamma and 1. And then the lattice operations join mid 0 and 1 are just the restriction of the operations in the L monoid. And so and vice versa, every positive MV-algebra, you can think of it, well, it is isomorphic to gamma and 1 for some positive, so for some conservative commutative distributive L monoid and some positive invertible 1 in N. Okay, so this gives us a good way to handle positive MV-algebras because these L monoids have a simple axiomatization. So for example, 0, 1 is a positive MV-algebra. It should be gamma of something. So for example, you can take R and the constant element 1. Also L3 should be gamma of something. You can take 1/2 Z with 1. What about the bounded distributive lattice? So take the 3-element bounded distributive lattice, so the 3-element chain, as a positive MV-algebra. So you set class to be join and times equal meet. And if you want, you can picture this in this way. It's also a subalgebra of 0, 1 times 0, 1. If you think of this coordinate being less or equal than this, then this is the set of order preserving functions to the two elements to the two element set 0, 1. This should be isomorphic to an interval of a certain lattice-ordered monoid. What can we take as a lattice-ordered monoid? Maybe there's a direct construction, but also we can, well, one option is to take, well, the set of pairs AB in Z times Z, where A is less or equal than B. And as positive invertible elements, you take 1, 1. In other words, we're taking the set of order preserving functions from the two elements posits X less than Y to Z. If you take the truncation of the constant function 1, you get you get the 3-element set 0, 0, 0, 1, 1, 1. In general, we can see every bounded distributive lattice has a truncation of a certain monoid, a certain lattice-ordered monoid. So, for example, take L, bounded distributive lattice, set classes join in times as meet. What is L the interval of? So we should find a certain L monoid. And one way to do this, well, there's a direct construction, but maybe that's not so easy to visualize, we can use duality. If you set X as the precisely dual of L, then L is the Klopen-Absatz of X, or in other words, these are the order-preserving continuous functions from X to 0, 1. And so maybe now you can guess what we can take here. What is L, the interval of? Do you have any guess?
0, 1 with Z.
Yes, exactly. Thank you. You take the continuous order preserving functions from X to that. And you take 1 as the constant function. And so you see L as the truncation of this lattice-ordered monoid. Thank you. Exactly. And okay, if you for each positive MV-algebra, you can find a canonical choice of M and 1 in M, so that A is isomorphic to gamma M1. And again, as in the MV-algebra case, this is characterized by the condition that 1 is a strong ordered unit, strong unit. So this means that for every element X in the monoid M, it's bounded from above and below by some multiple of the units, or the inverse of the unit. So there is some natural number N such that X is between minus N and N. If you add this further condition on the unit 1, then we get an equivalence, a categorical equivalence that we call positive Mundici equivalence. So on one side, we have positive MV-algebras and homomorphisms, so functions preserving all the algebraic structure. And on the other side, we have cancellative, commutative, distributive monoids with strong units and unit preserving homomorphisms. And these two categories are equivalent. So the way to go from 2 to 1, the functor is just apply gamma. And to go back, you use certain tools called good sequences. Okay, and this gives us a good way to handle. Let's see some axiomatization of certain algebras.
Abbadini algebras.
Yeah. Okay, so positive MV-algebras were defined as certain subreducts, but this doesn't tell us much about what kind of axiomatization we get. So, for example, Boolean algebras were a variety, bounded distributive lattices were a variety, MV-algebras are a variety. What about positive MV-algebras? Are they a variety or not? No, but your guesses, but no, it's not. They're not a variety. They're not closed under homomorphic images. But still they are a quasi-variety. That's fairly immediate because they are the subreducts of a quasi-variety. And also, what about generation? Boolean algebras were generated by 0, 1 as a variety, but even as a quasi-variety. Also, bounded distributive lattices are generated by 0, 1 as a variety, also as a quasi-variety. MV-algebras generated by, now here we replace the unity interval instead of the 2-element set, and this is a generator as both as a variety and also as a quasi-variety. In positive MV-algebras, again, they are generated by 0, 1 as a quasi-variety. But this just follows from this fact and the fact that positive MV-algebras are the subreducts. Okay. Okay, so if you have a quasi-equation and if you want to understand whether this holds, positive MV-algebras, you check on 0, 1. What about finite axiomatizations? All these three classes, which are varieties, where finitely axiomatized is varieties. Well, the best we can hope for here for positive MV-algebras is to get a finite quasi-equational axiomatization. And we have it. And that's one of our main results, that positive MV-algebras are axiomatized by a list of quasi-equations. Okay, let's see some of these equations. We get that a plus 0 and a times 1 are commutative monoids. A joining meet is a distributive lattice. Then both class and time distribute over both join and meet. And then we have these axioms that I'm going to explain. So there's a universal quantification of all the variables. So for all x0, x1, y0, y1, if x0 is the sum of y0, y1, and x1 is the times of the same elements. So what does this thing mean? In the context of bounded distributive lattice, so if you think this as join and this as meet, this is saying that x0 is a join of two elements and x1 is a meet of two elements, which is the same as saying x1 greater or equal than x0. So this is an MV version of x1 being greater or equal than x0. Sorry, yes, thanks. Thank you very much. X0 greater or equal than x1. Thank you. More outside the bounded lattice case, if you think of the positive MV-algebra as a truncation of a lattice-ordered monoid, this is saying that x0 is y0 plus in the lattice-ordered monoid, y1 meets the positive invertible element, and x1 is y0 plus y1 minus 1 join 0. So if you call y0 plus y1 y, we're saying that x0. So think of the lattice-ordered monoid as order preserving functions. Here we have the function 0, 1, 2. Y would be a function between 0 and 2. And x0 is the first layer. So it's y mit 1. Y x1 is the second layer. So it would be something like this. Okay, so x0 and x1, as you see, x0 is greater or equal than x1, but there's it's a stronger condition. And if you have this condition, then you have, in a positive MV-algebra, you have modularity. So you can rearrange the order of parentheses. If you have x0 times z plus x1, then x0 meet x plus x1. So these are the same, and this is in the lattice case. This is just so the hypothesis was that x0 is greater or equal than x1, and now we're saying x0 meets z join x1 is x0 times meet z join x1. So it's some MV version of modularity. And then we get this absorption property. I call this absorption because here you have x1 on this side, and here it disappears. And also, if you instantiate this at x0, at x0 equals 1, which can always be taken, you get z plus x1 meets z equals 0 is 1, so z. And if you look in the bounded lattice case, class is just a join. And even the absorption law. And then finally, we have cancellation. So for a lattice-ordered monoid, cancellation means cancellation property is this: x plus z equals y plus z implies x equals y. Right. Now, if you think of these as elements of the x, y, z as elements of the unit interval, then these might fail, the sum might fail to stay in the unit interval. So this might be a something between 0 and 2. And so to express this condition, you have to say that these two elements are the same in the two slides. So in a sense, this is can be thought as x0 plus z first slice, x0 times z second slice, and this in a sense is y plus z, y times z. So saying that these are coincide the same, x plus z equals y plus z, and x times z equals y times z. Okay, and cancellation says that if this holds, then x equals y. Okay, and this is an MV version of what properties for lattices? For lattices, this is x join z equals y join z, x meets z equals y meets z, implies x equals y. This is equivalent to distributivity of lattice. So cancellation is an MV version of distributivity of lattice. Good. And these are all quasi-equations. In particular, 1, 2, 3, and 4 are equations. Maybe 4 is not immediate that it's an equation, but you can rewrite this to show they are equations. The proper quasi-equation is this cancellation. By the way, if you remove cancellation, then you have a variety of algebras, and you're axiomatizing the unit intervals of commutative distributive monoids, which are not, might fail to be cancelled. But this is outside the scope of this talk. Yes.
I want to quasi-equation.
A quasi-equation, good, thank you. Quasi-equation, it's so you have, it's an implication. You have finitely many equations as it's an implication between finitely many identities and an identity. So, for example, here. Other questions? Yes. Okay, the first four. So these are the axioms of positive algebras, and positive algebras are. Let me go back. MV-algebras are precisely the gamma n1 for some cancellative commutative distributive monoid. Yeah? If you remove that hypothesis, then you get precisely gamma n1 for some commutative distributive monoid.
So when you say that monoid, you mean double monoid? Because you have the class and the time?
No, we have only one monoid operation, which I denote by plus. Yeah, I usually denote by plus. If you want to see it as a double monoid, sorry, if I go to the slide. the last slide. This one. Yes. So okay. So, but the fact is that in the monoids case, the two. In the L monoid case, the two are interdefined. So, if you have your monoid n plus 0, 1 join meets, then you can define x times y as x minus 1 plus y. This would be a monoid operation with 1 as identity element. Yeah, if you want, you can include this in the signature of this, and so 1 is invertible, so it's plus minus 1. Yeah, so I need to.
So these are pointed, double pointed.
Yeah.
One.
Yeah. Yes, that's fine. Yeah, probably it's better to see them as either this way or this way, where you can take -1, but -1 you can define it as 0 times 0. Yeah, I think if you want symmetry, you either take this signature here or this signature here.
Because the next is divided by
Sorry?
because the next is divided by cannot be out. We can make this divided by 1.
We have strong unit, right? Okay,
And the minus 1. And when
I'm not sure I understand.
it's going to be the old one, apart from that,
So what are the? I'm not getting the point.
and it's very much for me to have
Yes.
and you have a lattice.
Yeah.
So the signature would be for me going 5 and 1.
Yes.
That would be the signature and 1.
Okay. Yeah, for me, and since we're talking about commutative, the commutative case, I use 0 and 1. No, sorry, plus and 0. So this is a okay. So I think maybe we mean the same thing with So okay, maybe there are algebras without the cancellation property. Every algebra is isomorphic to gamma and 1, where M is the commutative distributive monoid without any, the signature is join meet plus 0, and 1 is a positive invertible element. Other questions? Okay, let's take a break. Okay, welcome back. So, as a recap, we had these two main results. One is that every positive MV-algebra is positive MV-algebras are equivalent to certain conservative commutative distributive monoids with strong units. And second main result is that positive MV-algebras have a finite quasi-equation axiomatization. Okay, there's one result I want to talk about. And let's start with this observation that by definition, every positive MV-algebra A embeds into some MV-algebra. Question. Is there a canonical embedding? Is there a canonical MV-algebra together with an embedding? Well, yes, for general algebraic reasons. Namely, the forgetful factor from MV-algebras to positive MV-algebra, since these are varieties, has a left adjoint. This is for general algebraic reasons. And so for each positive MV-algebra, we have the component of the unit that goes from A to B. And it's injective. Also, this is immediate because positive MV-algebras, every positive MV-algebra embeds into some MV-algebra. And so also the universal, so this universal map will be injective. Sorry? Yeah, so let's just okay. Sorry, what is B? Okay, sorry. This is the reduct of an MV-algebra. So,
But it depends on that.
yeah, it depends on H. Yeah, exactly. Yeah. So this is U, and let's call this functor U, and the left adjoint L. This is U of L of A. Okay. We call eta A, or simply the MV-algebra B, as the free MV extension of A. So there is this canonical embedding. So let's see an example. What is the free MV extension of the following positive MV-algebra? So what is the MV-algebra in which it canonically embeds? Well, we should find it is an MV-algebra in which it embeds. So let's see some examples of MV-algebras in which it embeds. It embeds, for example, in 3 times L3. So this might be a canonical, might be a candidate. Here I've added with gray just the pairs that I'm adding to get L3 times L3. But it embeds also in 0, 1, and 0, 1. So maybe this is the canonical, is the free MV extension. Sorry? Oh, yes. Oh, great. Good. Excellent. 1.3. Oh, yeah. Yes. Yeah. This is missing. Also, the following pictures, maybe no one is missing. Great, thank you. So in fact, it disappears now because I'm ashamed of this, but maybe, yeah, so 0, 1 times 0, 1, maybe another one, or maybe something else. Okay, we have this theorem, which tells us how to compute the free MV extension. Okay, so you start with a positive MV-algebra A, and any embedding into an MV-algebra B. So, for example, you can take the embedding of these into 0, 1 times 0, 1. Then you take the MV-algebra, MV subalgebra of B generated by A. Okay. For example, here the MV-algebra of 0, 1 times 0, 1 is generated by this algebra. Let's call this algebra the red algebra. Well, we get, since this in the red algebra, also its negation would be in the sub MV algebra generated by the red algebra. And then since these is in the algebra, MV algebra generated by the red algebra, and also this one, we can take the sum and we get this. I should also take for example, the inverse of this, and it should give me this, but I forgot to picture it. And this gives me L3 times L3, which is an MV algebra. So it's the MV subalgebra of 0, 1 times 0, 1 generated by the red algebra A. And the theorem tells us that this embedding is a free MV extension of A. no matter what embedding you start with. Right?
So the long diagonal,
Sorry?
the long diagonal would be there.
Yes, the long diagonal will be there. Yes, I forgot, but yeah, the long diagonal will be there. So, in fact, and it will be L3 times L3. So the free energy extension of the red algebra is L3 times L3. In other words, an embedding of a positive MV algebra into an MV algebra is free, is the canonical one, if and only if it is MV generated. This is the non-trivial status. Okay, we can. Yes.
Are all MV algebras free?
No. No. But by free, I mean, sorry, by an embedding.
Yeah, this is behind it. Like every. It's somehow. I mean, like this suggests to me that maybe every algebra is free because we are saying that as long as you are generating them and the algebra with positive and the algebra, then this is actually free generation.
Yeah, but it's a free generation modulo the equations that are holding the positive MV algebra.
So I'm now just like taking the reader of your positive and the algebra and just a set, right?
Yeah.
And that would be just a subset of the algebra, and this is another free generation. That's what that's. So I'm saying the signature of the positive and the algebra is important for me.
Yes, exactly. The signature is important. Yeah, good point. Maybe I'll return to this in a few slides. The signature is important. I mean, it's important that we have a large enough signature. Yeah, excellent point. I will use it. So this is okay. Another way to say this is that if I have X, a positive MV algebra A and an MV algebra B and an embedding that is generated, then there is an isomorphism that makes this diagram green. See, where L is the left numbers. Okay, yet another recurrent reformulation. An equivalent formulation is that there is a unique generating embedding. So if I embed a positive MV algebra into two different MV algebras in a way that the images generate V1 and V2 as MV algebras, then these are over A. Or another equivalent formulation using the universal property of the adjunction is that if I have two MV algebras B and C, and I have a positive subreduct A, which is which generates B, and I have a function from A to C, which is a positive MV homomorphism. So so A is closed under the positive operations and the function preserves them. Then there is a unique extension of this function to a homomorphism of MV algebras. I mean, uniqueness is trivial because this is generated. What is not trivial is that the existence. So, for example, these might have a computational advantage. For example, if I want to compute how many homomorphisms there are from L3 times L3 to a certain MV algebra C, I want to compute how many MV homomorphism, then I can take a positive subreduct of L3 times L3 that generates it. For example, these are the algebra, the ordinal sum. So important. You can check that this generates L3 times L3. And now the set of homomorphisms from L3 times L3 to C is in bijection with the set of homomorphisms of positive MV algebra from the red algebra to C. So while L3 times L3 has 9 elements, these has 5 elements. So when you want to check all the possible functions, you have to check less things. Questions? Okay, and now I want to get back to your comments. So for a general fact that holding subreducts of pre-varieties, what we saw before has an equivalent reformulation in more syntactic terms. That is, that every MV equation, so every equation in the language of MV-algebras, is equivalent when you test it for MV-algebras to a system of equations in the positive fragment. So, for example, I don't know, this equation here, x equals not y, is equivalent to this system of equations where the negation is not used anymore. We only use the positive fragment. Also, there's also some more complicated ones. Okay, but this non-trivial fact is that every MV equation can be rewritten as a system of equations where we use only the positive fragment. And so it's important that we have a large enough set of function symbols, because for example, if I took no function symbol, I mean, I consider the subreducts with respect to the empty signature, it wasn't true, it wouldn't have been true, something like that, that this is equivalent to a system of equations in the empty signature. Good. Questions so far? Okay, now I'd like to just mention briefly what is this general fact for subreducts of pre-varieties. And essentially, since in the particular example of positive MV-algebras, since these are intervals of monoids, certain lattice-ordered monoids, the property I told you before essentially boils down to a property of commutative monoids and abelian groups. So we have this fact that each cancellative commutative monoid M has a unique up to isomorphism, generating the embedding into an abelian group. Okay, uniqueness up to iso means that if you have two embeddings, there's an iso that make this diagram commute. So, for example, N embeds into Z, and yeah, if you have any embedding of N into an abelian group, which is generated, it will be isomorphic to Z. The key facts used are that if M is a generating submonoid of an abelian group G, then every element of G is a difference of two elements of M. And then use the fact that if you have an equation between two differences, then it can be rewritten in the language of monoids. And more generally, you have that any equations between two terms in the language of abelian groups is equivalent to an equation in the language of monoids. For example, so here, if I have this equation, or is equivalent, using cancellativity, I can add x and z on both sides, and I can rewrite this without using only in the language of commutative monoids. Okay, so, and the result I will mention essentially links this fact, which is more syntactic, with the facts before, which is more algebraic. So the same thing here is commutative monoids and abelian groups. If we add the lattice, an analogous fact does not hold without commutativity. So it's not true that a monoid has a unique embedding into a group. For example, you can take the free monoid on three letters, three element set, and you can embed it in a generating way, both into the free group on 3 letters and on the free group on 2 letters in an isomorphic way. And syntactically, this responds to the fact that this equation z equals x1 minus 1x cannot be expressed as an equation in the language of monoids. So the most trivial attempts will fail. For example, if I want to remove this inverse, the most natural idea would be to multiply y minus 1 by y. But in order to do so, I have to bring this x on the other side. So it would be that x minus 1. This is equivalent to this. Now I can remove this invert and by multiplying by y, but now I get the inverse here. So the trivial attempt to get rid of the inverse does not work. In general, it's not possible to rewrite this as an equation of in the language of monoids. Yes, something similar happens if we have the lattice structure. Then any cancellative, commutative, distributive monoids M is a unique generating embedding into an Abbadini group. And there are corresponding facts for terms. An equation between 2 terms in the language of Abbadini groups is equivalent to an equation in the language of monoids. All right, and yeah, for lattices, also this holds. We use distributivity instead of cancellativity. Yeah, let me skip these. And so the main theorem is the notion of a pre-variety. A pre-variety is a class view of algebras, which is closed under subalgebras and products. So, for example, any variety or any quasi-variety. And so, if we place ourselves in this setting where we have an algebraic language L plus and sublanguage L minus, and 2 pre-varieties plus and B minus for these 2 languages. I denote them with plus because this is richer than this, so because of this containment. And we assume that V plus contains all the L minus regex of algebra in V plus. So, for example, you take V plus as the class of Boolean groups and V minus as the class of cancellative commutative monoids. Yes. Or what's it called? An SP class. Closed under subalgebras and products.
Okay.
I think that's it. Is that correct?
This is pre-variety and quasi-variety is
Also closed under reduced hours or ultra products. So also the quasi-varieties are closed under subalgebras, products, and intra products. Is that correct? Okay. Okay. And yeah, the thing that we're using about pre-varieties is that they have the forgetful functor has a left adjoint. So there exist 3 algebras. So that one was we're using these facts. And then we can formulate the unique embeddability property given 2 algebras in V plus and an algebra in B minus. So, for example, you can think of these as MV-algebras. This is a positive MV-algebra. Then you have 2 embeddings, F and G, which generates B and C. Then there is a B plus isomorphism, make the following diagram commute. So we say that in the setting we have B plus, B minus. In this setting, we have the unique embeddability property if essentially any two generating embedding are isomorphic. So this is the algebraic condition. And the syntactic one, we call it expressibility property. And for each equation in the richer language, this equation is equivalent to a system of equation in the poorer language. So this is another property that in our setting might hold or not. For example, for abelian groups and commutative monoids, this holds, while for groups and monoids not. And the main theorem is that there's a unique method. I mean, these two properties are equivalent. Okay, and the main usage is we want to prove the unique embeddability property. I mean, the main usage is the trivial, actually, the easier direction. That is, if we prove the unique embeddability property, we want to do this, and we just show that the equations in the richer language can be expressed in the poorer language. For positive MV-algebras, we use both directions. So it was easy to prove that every equation in the language of binary groups can be rewritten in the language of monoids. Then we deduced that then each cancellative commutative distributive monoids has a unique generating embedding into an abelian group, a group. And then using this gamma factor, we proved that each positive MV-algebra has a unique generating embedding into an MV-algebra. Then using the other side of the equivalence, one can deduce that every equation in the language of MV-algebras can be rewritten in the language of positive MV-algebras. Yeah, this can be proved also directly, but it's not super easy. So to recap. So we defined positive MV-algebras as these subreducts of these MV-algebras. There were some bad things. I mean, it was not a variety of, I mean, first bad thing was the name. Then it was not a variety, but then there are some nice ones.
Not a variety, it's not so bad actually.
Okay.
Yeah. It's fine. It's quasi-variety, it's fine.
Okay. Okay. It's a quasi-variety. We have a finite quasi-equation axiomatization. This was our first main result. And there are intervals of certain monoids, and we have this unique embedding into MV-algebras, which essentially tells us that in order to be sure that something is free, it's enough to check that it's embedding and be generated. So some future directions which I want to explore, and also would be happy someone of you is interested to think together. So the first question I want to address is what makes Mundici's equivalence work? What is it that makes it work? So part of this work started with the observation that the negation is not that essential. It's not essential. For example, in the definition of good sequence, you don't use negation. But also the lattice operations seem to be not that essential. So also in the definition of good sequence, they do not appear. And so the goal would be to obtain an equivalence a la Mundici between certain algebras in this signature plus M01 and certain algebras in the signature 0 plus 1. So monoid signature plus this constant, also minus 1. If you want, it's a natural. I mean, yes, also minus 1. Or you ask that this is invertible. And then two unary operations, tau 0 and tau 1, where tau 0 and tau 1 are unary symbols. that you should think of as truncation by 0 and truncation by 1. And you kind of need it because if you have an L monoid and you want to define class, the truncated class, then you have to say x plus y meets 1. So at least maybe you don't need the lattice operations for between any two elements, but it seems that you need for to truncate at 0 and at 1. Okay. And I would like to do it without assuming the cancellation property. Not just because I think it would be nice to see bounded lattices that are not necessarily distributive as intervals of certain monoids. Of certain algebras in the signature here, right? And then distributivity would correspond to cancellation product. But I think it would be nice to see, just the join and meet of a lattice to arise from just a unique monoid operation. But anyway, this would not be just the case of bounded lattices. Just would be a specialization. There's a side question which I don't really know whether is there a unique generating embedding of class times 0, 1 subreducts of MV-algebras into MV-algebras. So, or equivalently, is every equation in the language of MV-algebras equivalent to an equation in this language? I don't know, maybe not. Maybe this equation, this condition, you can express it into this language, but I'm not sure. And yet a further step would be to go to the non-commutative case. In this case, I think here you would need to add 2 unary operations to encode how do you call it? This map here, the conjugation the conjugation by 0 and by 1. Probably. Yeah, I don't remember. I thought this the conjugation to put this to certain 2 conjugations that I don't remember right now. Okay, then second feature direction is to prove an MD version of Bloch's active theorem. But I didn't really give much thought about this, so better me not talk very much about this. Okay, a third problem, which maybe is the most interesting to me, and it comes from an input of a referee for an abstract of a talk, whether the characterization of the unique immutability property that I gave for varieties actually is an instance extend beyond algebraic structures to a general model theoretic set with where we replace equations by atomic formula. I don't know. Would be very interesting. And then also Łukasiewicz suggested maybe we have a duality at a later vein for positive MV-algebras. So I'll just show here the main results. Here are the works on which this talk is based. And thank you very much for being here.
Thank you very much. Very nice talk. Okay. Comments or questions?
I have a question. Okay.
Not about the
No.
Yes.
Okay. I mean, from the algebraic point of view, is anything known about this quasi-variety? I mean, what are the subreducts reducible? What are the quasi-varieties? The quasi-varieties, whatever. I mean, from the algebraic point of view. that has been studied somewhere.
Of what? Of positive MV-algebras.
But there are quite a variety of these and say whether the relics that we use more. Look at the last of the subvarieties, look at the atoms in the last of the subvarieties. I mean, the first question that comes to mind is preliminary. I mean,
It's generated as a quasi-variety by 0, 1. Does it answer the question?
This let's think that. I mean, what I'm saying is every algebra in the variety is subject product of totally ordered algebras.
Oh, okay. Yeah. Yes.
Okay.
So
it's pretty right.
Yeah.
But the problem is that since this is a quasi-variety, right? I mean, you don't have really. You're interested in the relative subject reducible. So my question is every, I mean, the finite subdirectly reducible in this variety? Do coincide with totally ordered members, for instance? Question like this, right?
Yeah.
Which would shed the light. I mean, what I'm saying is, have they been studied from this point of view somewhere?
Oh no, yeah, I don't think so. I mean, they were because they were introduced 4 years ago. So
Okay,
so no, in my thesis, I say something about. I mean, beyond the constellation property, I say something about the subdirectly irreducible ones, which are totally ordered.
Yes. You see, this is the quasi-variety. So that's the subdirectly reducible. They don't have the story, the entire story.
Yeah, I mean, without the constellation, they are a variety.
Yeah, sure. Yeah.
Yeah, I think,
Or maybe
these are the natural
another interesting thing might be studying the variety generated by this quasi-variety, which is commonly stated because it's lattice-based.
Yes.
And then you might actually reason, is this quasi-variety relatively non-distributed? That's another question that comes to mind.
Okay.
I mean,
Yeah.
my question was, if these things are already being done somewhere or not, probably the algorithm is not.
I don't think so, but thank you for the suggestions.
There are a lot of things you can do with the quasi-variety.
Extending to the non-competitive case, or I just wanted to make the comment that to essentially as in our paper about Mundici's equivalence to the Hitler and the MV-algebras, and he doesn't use good sequences to prove it. It should be quite interesting to look at how we can do it without that and with the words as well. I like the extension as well.
Okay. So you're saying that in order to do the non-commutative case, then one can take inspiration from the people by.
I think that those sequences approach it's quite quite technical. Doesn't do. I mean,
Okay. Okay. Yeah, I think it can work also with the good sequences, but yeah, suppose the technique. I would like to understand better how this other technique works.
There's all those some varieties of this quasi-variety. Right? There is some sub-varieties of this quasi-variety because for MV, there's only probably many sub-varieties.
Yeah,
a very unusual situation because it's not a chain, it's an interesting level and it's powerful. And is this possibly a critical case here?
I mean,
Good question.
The fact that it is because the fact that it is a quasi-variety actually changes things a little bit. Because I mean, quasi-varieties, I mean, it's much easier to find sub-quasi-varieties that behave exactly the way you want. because I mean you have the but my feeling would be I would simply like to know if the totally ordered are exactly defined in subreductive. That would be because I mean that would imply a lot of things. For instance, it would imply that it's a relative quantum distribution. Relative quantum distribution would imply that that's something that they already know, but we if we try to find the case, they already know it's found the case, but the structural reason why. And so on. But I mean, is you know, name aside their interesting knowledge.
So, equation being expressed,
Yes.
equation subject.
Yes.
Can you explain how many variables between the another?
You cannot add. Yes. So yeah, in the non-commutative case, also in the lattice case, there you don't have this expressibility property. I think, yeah, in a workup you kind of rewrite the equation, but you add a variable.
In groups, as you said, you cannot get rid of the inverse to the left side, but for that, even if the inside, there's a way to rewrite the column, you transfer one variable for inverse.
Yeah, you cannot add.
So you have to say that the kind of variable.
Yeah.
Also, when you said that equation given a syntax,
Yeah.
system equation, how generally how special involved with MV-algebras? That's the question because
So, I mean, in general, the theorem tells us that we have the unique embeddability property, if not if every equation can be expressed as a system of equations. In certain cases, you have that every equation is equivalent to just one equation, like for groups and monoids. You can always assume that you can always find just one equation. For positive MV-algebra, for positive MV-algebras and MV-algebras, the most natural way would give you system of equations. I don't know if you can combine them to a single equation or not. So, but your question is?
so if you have a system here for one line,
Yes.
and it's 25 variables among variables. How do you do it? Involved with
So yeah, you have a system. Can you make an example? Can you tell me an example of
if you have a system of equations, how do you replace it by a simple equation? So if it's involved with you have a system of equations.
Oh no, like in positive MV-algebra, every MV equation, so for example, is equivalent to a system of equations. So if I am given an equation in the MV language, then it's equivalent to a system.
And that system cannot necessarily be replaced by a simple equation.
Yeah.
So you ask it probably if there is an algorithm that have to pass from the system to the single equation to the other end. I think
No, that's whether can simplify the single equation.
No, I mean, but what he's saying is different. He's saying that if you have given equation, then you can find a system
Yes.
which is equivalent.
Yes.
What he's asking is, even a system of equation, can you merge it into a single one?
I mean, probably I can find that. But can I rewrite this in a system? Sorry, as an equation in which language? The MV-algebra or I don't know. Maybe not. I think I would conjecture not. I mean, probably also in the lattice scale, if you have a system of equations in the bounded lattice.
Because I'm wondering, now is that we can write it as the key to it, the one as the very maybe you can write it as a system with the same number.
It's a system of equations.
You're not thinking that you write it as a system, allowing us to have a system. That's something that we need to look at and not case, because then we can eliminate inverses. We can get a single equation, not trying to take into account we are one variable. But maybe we can rewrite that as a system of equation without the variable.
Okay.
I mean, it's not again, it becomes what happens if you allow variables, so the specific, the ability that becoming simple or the simple.
Yeah, then, okay. Yeah, but then we will not have this equivalence, I think. Yeah, we will. Yeah, I think we would have a different condition. I don't know what is if there's a nice algebraic equivalent. Thanks.
Other questions? Okay, no, thank you very much.